Thank you very much, Alfred. This introduction. It's a pleasure to all for. So this talk about this in the cloud. It's a kind of research that some of you. So given the audience, have tried this talk to be accessible, but specific. We can also have some references. You can. This is kind of broad over what. So my focus here is to look at these accelerators, give you some introduction to what's happening in this technology. Also show that there are some actual commercial platforms on which FPGAs today, like hyper, like GPUs, and also talk about some acceleration we this technology. Example problems. Again, as I said, instead want comparisons with GPUs, multi. What do we do? Happy to talk. So respond with and you will find these publications what I talk about today available on this website. Visit the website. Also contact me to go deeper into. So what today's talk I have approximately that. So I will talk about technology evolution here. This has been around for many months, almost now what's happened in this area. Talk about what people are doing FPGAs into the cloud. Then I will go into how to design accelerators, go through some examples. For example, graph analytics is an important area of research. A lot of FPGA accelerators are available in graph analytics. And this one more example here, people are very concerned about privacy and security. And FPGAs are being used here to do these kinds of example. You can do secure inferencing on the cloud without revealing your data. I'll go through an example of that and see how we can do real-time computations by using FPGA technologies to solve these kinds of problems. Number of other examples. I won't have time to go through all of these examples. I will also talk about what's happening in the technology in terms of where these FPGAs are evolving into just compared to CPUs and the GPUs in the market. So where I'm coming from, so the computing landscape is changing. By this, I mean that there's quite a lot of technologies that are evolving, applications are evolving. I'm just showing some examples here. We're all familiar with these examples. Surveillance cameras, you can do all kinds of data analytics in real time. Social media applications, you can do quite a bit on your cell phone today. That really in which you collect a lot of data and then you interact with the environment, go on the internet. So I characterize this as data is everywhere. And we do a lot of analysis in the loop, in the cyber physical systems, for example, autonomous driving here, you collect information, you make real-time decisions. This is happening at the edge of the internet. This locally computing that you do here. Real-time performance is important. And I call this as computation anywhere. You collect the data and you compute at that point, and that's where these kinds of accelerator technologies become very, very important. So what it means is that if you look at all these applications, we are going from traditional workloads to more data science related workloads. Data science, maybe an example of that is inferencing on the edge of the internet is an example of a data science application. So the big picture here is that you collect data at the edge, and then you correspond with the data center where you do your heavy computations, for example, and then the results go back to the edge of the internet here, and then you make your real-time decisions in the process. So what is happening here is that you do some really large-scale computations here, and this data has to be performed, these computations has to be performed in real time. Therefore, there is some latency here, maybe in the range of milliseconds latency here. Collect the large amount of data, you compress it, for example, send whatever metadata you want to send, make a decision here, and then go back to the edge of the internet. This is kind of the big picture of the problems we are trying to solve here. All the examples I talked about in the last slide, the previous slide, belong to this kind of a category where you collect a lot of data, compress it, make use of it, go to the internet, go through the internet to the data center, accelerate those computations, and come back to the edge of the internet. That's what I'm showing here on the outside set of applications we have. So the focus of this talk is that what do we do here in the data center to accelerate those kinds of computations, going beyond CPUs or even, for example, GPUs that is available in the market today. And if your latency is important, inference latency is important for you, what can we do to alleviate those kinds of problems. So to give a classic example of this is that today we use these large language models like ChatGPT, for example, and you ask the question in that context, do you want to get real-time performance for those kinds of generative AI models? And processors cannot get those kind of performance. You use GPUs for training, but GPUs are really good for batch processing if you're doing training on that. If you say that I have a large amount of data, a query is coming from the user, and I want to be able to solve this in real time, what kind of advances should take place in the data center here to get if the inference latency is what is important for us. That's the kind of problems we are going to be interested in. So concurrently with the applications, quite a lot of technology evolution has taken place in the last 25, 30 years. We are used to looking at processors becoming more and more powerful. Various kinds of computing fabrics I've listed here. One of the examples is the FPGAs, which I'm going to talk about in detail today. We are aware of CPUs and GPUs. There are also very large accelerators in the market today. You can get very high performance using these accelerators for specific data science applications. Along with that, quite a lot of memory technologies are coming into picture. I've just given some examples here. And finally, these are all getting integrated here. Various new technologies are coming here in terms of integration. You may be familiar with something called the CXL standard now that's coming here that operates on top of the PCIe Express that you have there. You can interconnect various devices by using a common protocol here, CXL protocol, in which we can kind of combine this into build more complex node level accelerators that you have for the data centers, kind of the way the technology is evolving. So in that big picture, the processor plays a role, but maybe the other technologies are probably even more important. That's where the FPGAs come into picture. So I'm going to go deeper into this technology here and then say in the big picture of the acceleration here, how these FPGAs could be used to design these accelerators and get a very high performance in that context. Just for the benefit of those who may not know FPGAs, I know many of you in computer science perhaps are not aware of this technology. The ECE students perhaps know about it. FPGA here stands for Field Programmable Gate Arrays here. This field programmable here means that I have various logic blocks. I can configure them. You can build functions you want. It is programmable interconnect. The connections between them can be programmed. And also the on-chip memory you have here, you can program it. That's kind of the programmable idea coming into picture here. So what it means is that these devices consist of very large number of basic building blocks. That's what I've shown here. These building blocks can compute any of those 4 input or 6 input functions. You can program them. You can get millions of basic building blocks you can get here, and then they can do simple logic operations, typically 4 input function. These days you can do 5 input and 6 inputs as well. They also have a local memory. It's like a unit bit of data that you can store inside those building blocks you have. They also have quite a bit of on-chip memory here, what are called static RAMs available on these devices here, plus very high on-chip bandwidth. You can connect these devices, these basic building blocks, by using extremely high bandwidth on these devices. Terabits per second kind of bandwidth is available. So this is the basic structure of the FPGAs you have here. So what is important is that there is no notion of an instruction set architecture. We're not talking about an x86 architecture or a data parallel like the CUDA programming model for the GPUs we have. Everything is completely under your control. You can design the hardware, you can design whatever systolic arrays you want, or you want to implement a CNN network, whatever is the application specific architecture you want, and you can do all of that in software. That's the key idea here. This hardware is given to you, it is configurable, you can build it, but you don't have to go and design the ASIC. The ASIC is given to you as a particular product to you. All you do here is programming it. That's why it's called field programmable. So in using software, you can control the hardware, you program the hardware, and then use that repeatedly for your inferencing or whatever is application you have in that context. These technologies, I just call them here, whatever I showed you in the previous slide is a basic technology. Technologies evolved over the last 25 years. If you look at a typical device in the market today, that's quite complicated. These devices from Intel and AMD, they are the ones who manufacture largest number of those more advanced devices in the market. There are a couple of other companies also in the market today. They have the basic building block. You can also get processor IP core integrated into them. You You can get static RAM. You can also get various hard IP here. For example, if you want to have a tensor block, Intel FPGAs today have tensor computations also. You can have quite a bit of external memory bandwidth is available. You can also get high bandwidth memory integrated into it. What is important is these devices sometimes even have higher packaging density in terms of number of transistors that you can get on these devices compared to what you can get for CPUs and GPUs in the market today. These devices are quite powerful, quite popular also, even though HPC community may not be using these devices, even though there are some projects that try to use FPGAs in high performance computing. So you can get IEEE 754 floating point units on these devices. You can get few thousand on them on a single device. You can also build accelerators for scientific computing by using these devices. I've just given some examples here. Two of these Xilinx today is AMD Xilinx, and then Intel. Intel is the other one that bought Altera several years ago. I've just given some examples here. These devices are quite powerful in terms of the kind of logic cells they have, about say 10 million logic cells. I talked about the basic building block. You can get 10 million of them on a single chip. Quite a bit of number of, let's say, if you want to do AI operations, machine learning operations, integer arithmetic, if you want to do 8-bit arithmetic, 38 teraops per second, that's a teraop floating point, integer operations, 8-bit arithmetic you can do here. Quite a bit of on-chip static RAM is available on these devices. Just given some example of what's happening in these devices. And these devices, if you look at the raw compute power in terms of what they can do for these kinds of operations, they're quite comparable to the state-of-the-art devices you have in the market today for CPUs or GPUs in the market. Just that many people are not aware of it, particularly coming from an application perspective. People sometimes feel that these devices, if you want to program them, you need to be a hardware expert. So I give some examples. You don't have to go through the hardware expertise to program these devices today. For example, you can write programs which looks like the OpenMP program you write using for scientific computing by using some simple commands inside that, similar to OpenMP. Can program these devices. Along with this, there are quite a lot of initiatives in the market today. Various companies are coming together here. This consortium of companies that is promoting use of FPGAs as an integrated accelerator in these data centers. There's quite a lot of standards evolving in the market. Various protocols are available here, so that for the various classes of applications here, you can actually integrate them into your C program or the PyTorch program you have here, and then directly run your code by using these kinds of back-end processing technologies that gives you an integrated view of these systems. Just giving one more example of the software stack here. If in just an example from the Xilinx, AMD Xilinx, and then in this case here, there are various libraries available on this. You don't have to write code all the way from a high-level machine learning application today. You can directly compile them into the FPGAs in the market today. It goes through various layers here, and finally here it will directly interfaces using those CXL, CCIX standards I talked about here. And then so you can develop, for example, you can directly go from these kinds of high-level languages here using this integrated software development frameworks. You get this fully integrated cards. You can just put them into your motherboard and then FPGAs, and then directly access them by using these kinds of software tools that can get a complete integrated system. So I mentioned about the high-level synthesis. So previously we used to write these programs by using Verilog or VHDL, high-level the hardware programming languages. You don't have to go along the route at all. You can directly write your code, C++, for example, insert the similar to the OpenMP commands inside that, and then you can completely compile that into the hardware you have. The hardware is fixed, but you can configure the hardware by using this design flow here, by using the high-level synthesis design flow in that context. Just giving an example here, HLS features here. In fact, whether it is Intel or AMD or even if you look at Microsoft, they use FPGAs quite heavily in their data centers, have high-level synthesis. And the language looks something like this here. Something similar to what you're used to seeing in the context of pipeline programming. And if, for example, if you do loop optimizations, loop parallelization in OpenMP, use similar commands. You can specify where you want to optimize in terms of the pipelining, how much resources we want to have. You can specify how large a processing element you want to have. For example, if you're doing today, if you're implementing say a CNN model, a deep neural network model, use this matrix algebra operations, use a tensor core, you do systolic arrays, you can automatically generate those kinds of systolic arrays by using this high-level synthesis. Want to pipeline here, how much of computation and communications you want to do. There's quite a lot of opportunities here for us to be able to optimize performance. I'm just showing here an example of using high-level synthesis and then generating actual systolic array for the implementation for let's say for 32 by 32 matrix multiplication systolic array and a single FPGA device here. I'm comparing here what happens if you were to use a high-level language, register transfer language, RTL language like Verilog, and then compare that with high-level synthesis. Very quickly you can generate highly optimized code. This is the kind of the performance you can get here in terms of the speed up you can get, gigaops you can sustain here on these devices. You can get extremely high performance. Parallelization is fairly easier to do today using these high-level synthesis tools. So if you are a software programmer, you don't have to learn these hardware programming languages, Verilog or VHDL kind of languages. You can directly go using these high-level synthesis tools and get extremely high performance here compared to what happens on a multi-core platform or what happens on a GPU as well. And again, you get these kinds of high-level performance without using batch processing. We're not using batch processing here. For a single instance, can I get higher performance? I mean, you're looking at a single instance, inferencing you want to do, and can you parallelize that as opposed to multiple batch processing of instances you may typically be used to doing on the GPUs. I've just compared here, just a chart here. It's quite a lot to take from one chart. So I'm comparing here the various technologies in the market, FPGAs, multi-core, GPUs, and also some of the accelerators in the market. Some of you may be familiar with this one, this Cerebras wafer scale integration engine. It's a very large engine here. Quite a lot of accelerators tied together by using wafer scale integration, one of the largest AI accelerators in the market. I'm just showing here for comparing the FPGA state-of-the-art devices, multi-core platform, and a GPU here, A100 GPU here, and then what happens in the context of a very large accelerator in the market today. So I'm just going to go through some simple examples here. If you go FPGAs here, you do fine-grained pipelining kind of is the way by which you. And then if you go to the on-chip bandwidth here, like 8 or 16 terabits per second is possible. The power dissipation here, typically about 1/4 of what happens in the context of processors and GPUs. Of course, this particular device here takes quite a bit of power here, 15 kilowatt accelerator in the market. And in fact, one of the applications for these kinds of accelerators is in the real-time inferencing. If you're doing very large language models and you want to get very high inference performance, these kinds of devices or the FPGA devices are strong contenders in that context. And then if you look at the number of transistors used in the state-of-the-art FPGA devices, talking about 30 to 40 billion transistors here. Compare that with the multi-core, about 8 billion transistors or 50 billion transistors in a particular GPU in the market today. So these devices are kind of in the market. They have been around for many, many years. To some extent, they are not as popular as GPUs for some reasons. I'll go into some examples of that. But in the context of getting real-time performance, energy-efficient performance, context of getting realizing cyber physical systems in the context of edge computing, FPGAs have a lot of potential. Lot of applications are being composed here, and that's where there's some of this AMD and Intel integrated platforms offer those kinds of opportunities for us. Also, these FPGAs are in the cloud. Some of you might have used it. It's available. In fact, if you are a graduate student, you can go to the Amazon website, Amazon AWS website, and then you can request it. They'll give it you for free for a few $100s of use. You can do some projects. In fact, that's what my students do. When I offer these courses, my students sign up on Amazon web services, and then we don't have to worry about any of the lower level tools at all. They are not hardware programmers, they're typically computer scientists, they're application developers, and then all these frameworks I talked about, high-level synthesis or the Xilinx Whiteys framework or the Intel frameworks, they're all available on this platform. So it is Intel, either it is an Amazon platform or a Microsoft platform, you can get access to these devices. Typically they have multiple and then various configurations. You can get them here in terms of FPGAs being integrated into the processors. You can get them integrated using the PCI Express. Again, all this is behind you. You don't have to worry about the actual hardware interconnections between the FPGA device and the processor device. And also I'll talk about some of the newer programming models that's coming into picture. You can kind of program on these devices here using one single C++ code and then specify where you want that compilation to go into. So if you talk to, say, people at AMD or at Intel today, they are the ones who are building these large FPGAs. They're integrating them into their own processors. They're also developing their own GPUs, as you know. So in those programming frameworks today, you can do the complete heterogeneous computing I talk about here. You can go to your cloud platform, different kinds of nodes, inside each node different kinds of processing, data parallel programming if you want to do, or FPGA AC kind of programming you want to do, or the CPU task parallel programming you want to do, and you can integrate them by using a single programming model. For example, Intel has the programming model called One API. I'll talk about it. One application program interface for various hardware accelerators you have in the system, including multi-core GPUs you have in the system. So it's kind of a very exciting time if you're doing parallel computing, parallel programming, heterogeneous computing. If you want to use hardware also as part of it, there are unified ways to get this very high performance by using these devices. Another example here, Microsoft Azure. I told about Microsoft platforms. So you can get access to these machines in which FPGAs are integrated into the network interface card. So therefore you can build a complete distributed computing platform by using FPGAs. It's kind of a very large set of devices that you can interconnect them here. They also have their own operating system available on the Azure platform here, where you can also rent these kinds of devices and develop your software. There's also a software defined networking interface available on top of it so that you can build some kind of a interconnected distributed computing platform by using FPGAs. This is another example here. I've just shown some details of what happens on the Amazon EC2 F1 instance here. You can get various kinds of usages here, various kinds of FPGA instances you can get, kind of shown here, the cost here per hour of renting these kinds of devices on the market here. And if you go to the Amazon website, Amazon AWS website, like I said, graduate students can get access to these platforms. And the whole hardware is hidden from you. You don't have to worry about all the details of Verilog programming, CXL interfaces. You can run your code from high-level programming languages. You can have your data science or machine learning interfaces, and you can directly compile hardware. And then I also mentioned that if you go to AMD Xilinx website, you get literally tons of libraries available. Integrate them into the platform, and then you can literally by press of a button using these unified programming languages, you can directly access the hardware from the high-level programming languages that I mentioned about earlier. So what I want to do in the rest of the talk is just go through a couple of examples. What can we do with this kind of technology? What kind of performance we can get? I'll go through two examples here. Again, at a very high level, just to illustrate here the kind of opportunities, the challenges you have in terms of using this technology. And finally, I'll conclude by going through some of the newer ideas that is coming in the market in terms of programming languages, in terms of the hardware platforms that's becoming available in this context. So we have been doing a lot of work in this space for the last almost 30 years. In fact, in the 1980s, we defined a model even before FPGAs became popular. We call them reconfigurable computing platforms, reconfigurable meshes. It's kind of an idea in which theoretically what can you do if you have reconfiguration available. So if I'm able to reconfigure every clock cycle, can I do some things faster? That's the kind of questions that community asked. So we know, for example, a computing exclusive OR is a very complex problem. If you want to compute exclusive OR very, very fast, it's used in many of the communication networking applications. Takes a lot of resources, like it's got an exponential number of gates you need if you want to compute that in a very, very fast manner. But if you use a reconfigurable computing model, so these are all kind of results we showed in the 90s, that solve such problems very, very fast because of the particular model of computation reconfigurable meshes provides, in which if you can reconfigure that in constant time and you don't have wiring delays coming into picture, you can solve some of these very high complexity problems very quickly by using polynomial amount of resources. That's kind of the ideas that came out in the 80s and 90s. But what we're doing here is more practical in the sense that we want to use the real FPGA devices. These FPGA devices, when you compile the hardware, their clock rates are not very high. Typical clock rates you get on the FPGAs today is in the maybe 200, 300 megahertz clock rate. Compare that with the CPUs, which probably runs about 10 times faster if you have CPUs and GPUs. In spite of that, if you look at the amount of parallelism that you have on the FPGAs, by effectively using those resources, you can get very high performance. That's kind of what the accelerators do for us. So in our own research, we abstract this into various models and then use this hardware software co-design loop here to map various applications. I'll go through example applications we have here. So the key word here is defining these models so that it captures the performance or the device characteristics. That's what we do in the modeling here, and then use that model here for our algorithm design, do the mapping by using the software tools here, and then we iterate the process here so that we can do this hardware software co-design and get high performance in those implementations. So we can define various models. Classic models that we can borrow from parallel computing and use those models to be able to design faster algorithms, accelerators, by using this FPGA technology here. So the approach we have taken in my research group over the years is to define this algorithmically rigorous, rich family of algorithm mapping that we can do here by looking at the applications, optimizing the performance. Optimizing the performance means that you have the FPGA hardware available to you at the level of those building blocks we have, the logic, the interconnections, the on-chip static RAM you have on those devices, plus the memory hierarchy we have. So we have to define the virtual architecture for that. There is no processor, there is no CPU that we're talking about here. That means you have to define that, do the actual mapping, scheduling you want to do on that. That gives you high performance in that implementation. That's what is the hardware software co-design approach I talked about. So I'll go through a couple of examples. I've taken 2 examples here so that I can illustrate to you the kind of performance we can get by using these FPGA devices. I've taken 2 examples here where this kind of actual implementations is happening in the cloud platforms. People use these kinds of accelerators today. I'll go through one example here of graph analytics, which is an alternate way of doing a lot of applications today. People represent relationships, graphs as the basic structure for representing a lot of information, and then you perform operations on the graphs to make some decisions as to what that means. For example, you may have a very large social network graph and you want to understand, maybe build a recommendation system on top of that. That's where this graph analytics comes into picture here. I've just given some list of our previous papers here. Any of you interested can go deeper into it. You can also access them through my website. So the basic premise of graph analytics is that you represent information by using graphs, could be directed, undirected, and then you extract some properties of this graph representation, which in turn corresponds to some real application problems you want to solve. Application problems you want to solve, for example, if you look at graph machine learning, if you have a particular node in the social network, for example, on Facebook, can you tell me which other users are of similar personality on the Facebook? This is a classic problem, graph machine learning problem. I will not be able to go through it here today. There's quite a lot of research, talking about if you have a social network, can you characterize nodes in the network? Can you characterize people saying that what kind of recommendation should be made in the system? So I am on Facebook. I get various recommendations from Facebook and Meta. I always wonder, what does the system think of me? It makes all kinds of recommendations. It gives me, it also has figured out my political inclinations. I get the kind of specific emails, specific recommendations coming from Facebook. The point I'm making here is that this is a large graph representation. The system wants to find out something about the users by at certain kinds of your behavior on the system, and those problems are mapped as graph analytics problems. And FPGAs are a very important technology that is used here to be able to make those kinds of conclusions. And that's where these kinds of problems come into picture here. There's also another important area of research here, what's called streaming graph analytics. In fact, many of these recommendations, the system would like to make that in real time. So an example of that, you walk into a shop, you walk into some your favorite shop, then a shopping mall, and the system instantly wants to make recommendations to you based on your previous history and the fact that you are in that shop, right? It's got the location information also. And quite a bit of graph analytics techniques are used in that context. Graph machine learning techniques are used to build those kinds of recommendations. And the data is a streaming data. There is data coming from those cell phones into the system. It's coming in at a particular fast rate, and the system wants to recommend to you at that instance in real time what possible products you may be interested in that particular shopping mall that you're currently at. So this is all the kind of problems that people are interested in solving. In fact, there are graph databases available here. You represent information as graphs and then you extract, make decisions. There are commercial tools available. For example, these are all commercial databases in the market today that use graph representation. In fact, if you go to this meetings here, MIT Lincoln Lab has a particular symposium every year called the Graph Exploitation Symposium. So this really asking questions, if information is represented as graphs, what else can you do with that? There's quite a lot of interest here by using these representations. Involved in this project several years ago with the US government, DARPA agency had a large program on accelerating graph analytics. In fact, they have one more new program by IARPA agency, which is looking at how do you build newer architectures that can be used for accelerating these kinds of real-time decision making that is based on graphs. And then we propose to use FPGAs in that context. Just examples of the kind of problems that this graph structuring, the graph abstraction can be used for solving. For example, you can look at your Google Scholar as a network, look at various kinds of protein interactions. You can represent them as graphs. And then typically the problem here is these are very large graphs. We're looking at graphs having billions of vertices and tens of billions of edges, and you want to be able to solve problems very quickly in the context of the graph analytics kinds of solutions we have here. Just an example here, what you can do using FPGAs. In fact, this area of research has been active. In fact, there are commercial companies that produce graph analytics platforms. There is quite a lot of activity in the VC space now. New companies are coming, building accelerators. In fact, people are talking about adding extra features into the traditional processor architecture so that we can handle these kinds of irregular problems, graph analytics problems. One important area here is what's called graph edge-centric paradigm, which is one of the techniques that is used to represent graph algorithms, where you can look at them as there are nodes and edges. You propagate information along the edges. That's what is the edge-centric paradigm here. Do this propagating in terms of broadcasting, collecting information on a large graph, and you repeat that so that you solve a very large problem. That's kind of this general idea here, what's called scatter and gather operations here along the edges, and then you collect the information, repeat that, so you solve a particular problem. So if you're doing graph machine learning, for example, when you do scatter and gather, you define what is the target of my scatter operations and what is the feature vectors that you go through, how many layers you have in the machine learning. So we can represent all those kinds of problems by using this very generic framework here, scatter, gather, what's called edge-centric framework that we talked about. So what you can do here is that for these kinds of problems, you can define application-specific architectures by using FPGAs. That's what we did in this research. We built this that can be used to configure the FPGA here, and then a memory controller so that you kind of optimize this memory controller. We also built a memory controller here for this specific application. So what happens here in our framework, in that you can specify your particular solution by using this paradigm. Large class of problems can be specified by using this paradigm. You can give the data about the target platform or what kind of device you have in the target hardware. You can also give some various design parameters, and you get optimized Verilog code that context. And this whole process was written by using high-level synthesis, so that so as developers of this platform, we used high-level synthesis, but as the end users, it's a tool. You specify the particular problem by using the solution space you have here, and then the system will automatically compile that into a highly optimized accelerator to run on the FPGAs. So just to go through some details of what happens in this hardware, just to get a sense of the optimizations you do here. Part of the problems is graph partitioning and data layout. The critical problem you face here, which is true for general purpose computing as well, is the memory access. A lot of problems you are not doing very like in a dense algebra problem. So typically these are all sparse computations in which if you bring a data value here, you do amount of operations before you throw it to data reuse is very small. So we developed various parallelization here specific for the FPGAs, where you talk about bringing those clusters of values and then partition the input graph into those large number of clusters, bring those basic unit here, and then work on those partitions. That's where you propose this particular technique called graph processing over partitions. This particular technique we proposed because when you have a very large graph, you are executing them on a data center scale processing nodes you have. Each individual node has FPGAs inside that, and the whole graph is probably distributed over several nodes you have here. That's where we call this as partitions. Each partition corresponds to what you do inside a particular node. The node consists of processors, GPUs, and FPGAs is a typical cloud platform configurations we have here. And that is a context under which we try to minimize the total amount of communication we do. So the critical problem here is the external memory access in terms of the number of accesses you do, as well as the complexity in terms of the irregular memory accesses you have. That's kind of the classic problem to be solved here. And for that, the solution we proposed was to use a particular data layout, which I will not go into the details. The critical problem is that when you traverse those edges, that's what is the edge-centric paradigm we talked about here. You do a large number of memory accesses for the scatter and gather operations you have, and then you can show that in the worst case, number of operations you do, number of memory accesses you do is proportional to the number of edges, which is the size of the input problem we have for the graph representation. So we come up with techniques by which we can take these kinds of irregular communication patterns you have here and regularize them by using particular data layouts, and that's what gives you, eliminates many of these random accesses and gives you very high performance in those implementations. That particular optimized data layout here is specific here by doing some initial processing on the graph here, a particular way you represent the graph by using the adjacency list representations you have that can give you high performance in the implementations. So I will just skip this theorem here. What this is telling you is that if you execute this program on a large data center collection of nodes, it is telling you that we can reduce the total number of memory accesses, which is proportional to the number of edges, which is in the range of tens of billions of edges you have in a typical graph, to something that is a small quantity here, which depends on the number of partitions. Number of partitions corresponds to the number of nodes you are going to be using in the data center. So we can make it small. We can take this very large graph access patterns you have and convert that into a smaller number of bucketed access patterns. What the buckets you have here, I call them bins, and then that reduces the overall memory access cost that comes into picture in those implementations. So if you put all of these things together here, this is what happens here on the complete data center scale processing here. You have a large graph that is partitioned across the various nodes you have. These are all the individual nodes in the data center. You create these bins for asynchronous communication between the various nodes you have here. Inside the nodes, you use FPGA accelerators and reduce the traffic between the processor and the local memory as well as processor and the remote memories. And these are the communication you perform here, which is performed by using that previous where I said we can reduce the number of communication operations to order of k squared, where k is the number of partitions you have. That is the number of nodes you are going to be using as part of the data center implementation. Let me just go through some example, what kind of performance we can get. We implemented this by using a particular platform. This is a card that you can get purchased from Xilinx, AMD Xilinx, in which you have the complete FPGA plus local memory, and then you get the whole card for about $5,000. You can buy it in the market today, and that's what is one of the data center accelerator cards here. That's what we used here. And then I'm just showing here the various graph algorithms that we implemented. These are all can be represented as classic problems, matrix vector product, sparse matrix computations, dense matrix computations. By using these applications, you can also implement the various versions of graph machine learning, which are very, very popular techniques today used here on graph analytics problems, looking at some recommendation systems, for example. So what we are able to do here is that I've just listed here the various optimizations we performed here. Just a reference here if you're interested to go deeper into this graph analytics on FPGAs, and then what is the kind of performance improvements we can get here compared to what happens on CPUs and what happens on GPUs here. So typically when you implement this here, as I mentioned earlier, these FPGAs have a much lower operating frequency, about 1/10 the operating frequency of the CPUs. In spite of that, by effectively using those on-chip resources we have on the external memory bandwidth on these devices, you can get extremely high performance. In fact, what we did was that after we did the application-specific architecture on the FPGA, we worked backwards from there, whatever techniques we were doing here in terms of the processing pipelines we built, and then we map them back onto the GPUs. In fact, you can get very high performance GPU implementations also by using our notions of pipelining as well as memory controller that we designed in that context. So let me move on. So I would like to take one more example, which is a very practical example in the context of data centers, and then conclude the talk with what happens in the future, what kind of technologies as the technology is evolving. So I would like to look at this area of research here called homomorphic encrypted computations here. In particular, we would like to look at the CNN inference problem. And the challenge here is that if you're looking at these kinds of inference problems, the end users are concerned about the privacy of the data. And one of the emerging technologies in this context is the homomorphic encryption, in which the users can encrypt the data and send it to the cloud service provider. And the other side of it does not know what the data is. So you feel comfortable, feel confident that your data is secure, it is private, what's called privacy preserving computations. So in this context, we are using FPGAs here to be able to do this kind of inferencing problems at extremely low latency, real-time performance you want to get here in data centers, in which you would like not to reveal the complete data to the other side to the data center. So this homomorphic encryption is a very important area of research. In fact, there is last 20 years of research here. It was proposed in the beginning of 2000. And people have not looked at this problem from a practical point of view because computationally these are very, very demanding problems. And then so people have not implemented it. So today there is a lot of interest here. So you want to be able to, as a user here, so you're going to a cloud platform. These are the end users who have some data that they want to compute on the cloud. The examples I talked about earlier, you're collecting data on the edge of the internet, and then you want to compute using the accelerators available on the data centers, but you don't want to reveal the data. So you encrypt the data here, send it, you perform all the computations, and they get the result back here encrypted with the property that the cloud does not know what this data is. We're not decrypting the data here on the cloud. The data is encrypted, and you perform all the computations on the encrypted data, and then you get the result back in that encrypted space. And then you as the user here, you have the decryption key here, and then you only have access to the result. Nobody else has access to the result, right? So in this context here, this is what is the fully homomorphic encrypted computations, FHE here, which means that you can encrypt the data, do all your computations in that encrypted space, get the result back in the encrypted space, and the user will decrypt it. So the computer in the data center here does not know what the data is. It's all fully encrypted. That's what is a fully homomorphic encoded computations here. So we're not going into the details here, the specific operations we do here. All the data is represented as polynomials. High degree polynomials are used here in this context. What it means is that these computations are quite expensive. Quite a bit of extra work is done here, and that's where acceleration becomes very, very important in this context here. Now, I'm also focused here on looking at a classic problem here. If you want to do CNN inference, and the CNN inferencing that you want to do here, in which you don't reveal your data to the data center. You collected some data at the edge, and you want to do some inferencing. It could be your chat GPT kind of a problem, but You don't want to release what that particular data set, whatever data that you have, whatever query is coming to at the internet, that you don't want to release that. So the particular threat model here, threat model you can talk about here, how much you want to preserve here. So we can, for example, look at the case in which the input and output are private, it's encrypted. The data center will not know what the data is, and that's what is private to you. The model is kept on the server. So the language model, for example, is on the server, and then that is not encrypted here. It's an example of a particular, there are various versions of the threat model that you can solve the problems. And we're taking a simple case here in which the user knows the data, and the server will not know the data, but the server knows the model is going to be encrypted, right? This is what I've shown here, what happens in a typical CNN inference for the various layers here in terms of comparing. If you do the computations by using the fully homomorphic encrypted notations you have, or the unencrypted space here, and that's the vertical axis is the amount of time that you would spend here in terms of the data sets that's going to be accessed in this context. The important fact here is that because of the representations, it's quite a bit of the memory footprint that comes into picture here. Quite a lot of memory is used here. You have to essentially take this inputs and encode them into a large space. That's where the polynomial representation comes into picture. For this example, for a particular security level, what we observed here is that up to 40x increase in the amount of the data traffic that comes into picture when you implement these kinds of applications, plus extra computations you do in that context here. So there is also quite a bit of CNN implementations in which homomorphic encoding is done. That's what is the example that we're considering here. And then we're looking at the case in which the model has been compressed. This is a sparse model, and then you want to use fully homomorphic encoded computations in that. And then can we use FPGAs in the context? Can we do high performance real-time inferencing in that context here? So the key problem here, as I mentioned, is that we have very large amount of data sets, and you want to be able to carefully organize the computation so that I reduce the traffic to the external memory in the systems. All the data is not going to be, you can't save them on the FPGA resources, you can't save them on the cache memory on the systems you have here. You have to go to external memory, and you should reorganize your computation so that you can get data reuse that comes into picture that can give you very high performance. I've just listed here what happens if you try to do these kinds of computations. The simple threat model. You have the data, you want to encode it. The server has the complete CNN model. For example, in this particular example, we are considering the model is not encoded. If you do here, large amount of data movement comes into picture. Irregular access patterns, the sparse CNN patterns comes into picture here. Plus, we do quite a bit of modulo arithmetic in this context. All these are all polynomial arithmetic operations you do. For example, you might use number theoretic transform to be able to multiply numbers in that space here. So these are all the kind of challenges that comes common to CPU and GPU. This is not nothing new. These are all very specific to how the fully homomorphic encoded computations take place here. Now, if you go to the context of FPGAs itself, so there are a number of other challenges you face here in terms of designing a highly efficient accelerator. So keep in mind that we do not have a processor architecture that is available to us on the FPGAs. You have to design it yourself. And that's where the challenge, opportunities for that for you to be able to do it here. So we can do data flow optimizations here. We can look at the kind of data reuse that comes into picture and design specific architectures in that. That's what I call them as opportunities. These are all challenges in the context of CPU and GPU. We can convert them into opportunities and exploit the FPGAs in that. We also need to do conflict-free scheduling here. I talked about the memory bandwidth becomes a critical issue here. So we can handle this irregular memory accesses by carefully scheduling those accesses to the external DRAM you have in this. Plus, finally, we have fine-grained control. We can specify our own mapping and scheduling algorithms. That's what we did in this particular example, which I will not go into details, but you can look it up from my website. I'll just go through some example here, compare the performance we can get. In fact, if you go to the Microsoft website on their cloud platforms, there is a library available for FHE. It's a C library here. It is written in OpenMP. So you can run this on the CPUs here, and then we are comparing the performance using the FPGA implementations we have, compared that with the CPU implementations that is obtained by this highly optimized C library, that is a C library it's called. which is available on the Microsoft platforms here. So I'm just showing here the comparisons. I will not spend much time here. What is shown here is for the various layers of the CNN network for two different kinds of CNN models we have here. And the vertical axis is the speed up that you get here compared to the CPU baselines. CPU dense and CPU sparse, two different standard model and the compressed model for that here. And then I'm showing here the kind of speed ups you can get by using FPGAs for using the various optimizations, which I did not go into today, but you can find them at the publications I talked about earlier. We do a number of optimizations by actually designing the virtual overlay architecture for it, talking about the scheduling optimizations to reduce the traffic to the external memory you have, to reduce the conflict to the external memory you have, and you get quite impressive speedups here. In fact, here, if you compare that with the V100 GPUs by using these FPGAs, you can get very high performance for inferencing applications. Inferencing, I'm not doing batch processing yet. For a single instance, I give you the data, get me the inference from the cloud and come back to me. Not collected thousands of them and gave it to you at the same time. This is very important for edge applications. There are cyber physical systems kind of applications where you are in the loop and you get the data and you want to quickly make a decision on that, and you want to be able to use this secure and privacy preserving computations here, and then you can get very high performance. I also made a comment here that these problems are all bandwidth limited problems. The higher the bandwidth you give, better the solution you can get if you can effectively use the bandwidth. What I'm saying here is that this particular GPUs have extremely high bandwidth compared to what happens on this FPGAs. FPGAs typically have about 32 or 64 gigabytes per second is the external memory bandwidth you have. You can get 10 times more bandwidth on the GPUs, for example. In spite of that, you can get much higher performance on this FPGA platforms by using this specific implementations. Let me move on. Take 5 more minutes. Is it 5 minutes here? Okay. So I just talked about this FPGA revolution that is taking place. In fact, there are many conferences that look at this technology in detail, but this is also kind of getting into the next level here, where you can get a complete device like that in the market today. If you go to AMD website, you can get a device that's got kind of all kinds of parallelism built into one device. The ACAP devices in the market today. You can get processors. In fact, you can get various real-time processors here. ARM processors are integrated. You can get adaptive engines called FPGAs, whatever I talked about earlier. And you can also get what are called intelligent engines. These are nothing but data parallel programming. These are all the GPU engines you have. This is implemented by using the RISC processor course that is available here. All these are in a single device. So you can get very high performance in this. You can get GPU if you want. You can also interconnect it here by using the on-chip interconnect network on chip here. You can program this device, and there are newer programming models that are available here to be able to get extremely high performance. Plus, you also have access to high bandwidth memory. You can do this devices you have here. Plus, you have the usual PCI interfaces and the Ethernet interfaces here that can be used to get high performance. And this is the amount of accessible local memory here. If you want a gigabyte of external DRAM on these devices, you can interface them and access them through the scalar engines or the processor engines or CPU engines that you have on these devices. So if you look at this here, I just put this table here to see the kind of hardware features in these devices. It's mind-boggling. Something that unimaginable few years ago in terms of the kind of latencies, the kind of bandwidth you can get. Single device today, in the market today. Very large number of RISC processors on a single device. You can do data parallel programming with that. Quite a lot of bandwidth available on the device here in terms of the FPGA CPU. You don't have to worry about the PCI Express and the CXL interfaces. Everything is on the single device itself here. And then quite a lot of external memory bandwidth here in terms of accessing the local DRAM or the Ethernet switches that you want to access through that. In fact, if you look at what's happening, I just gave the example of what AMD is doing. And if you go to what Intel is doing in this space, you can get these completely heterogeneous architectures, tightly interconnected at the node level of a data center, for example. You can talk about multiple sockets. socket having multiple GPUs and FPGAs. So we can look at this as really a system like this you can buy in the market today. A single node like this can have maybe terabytes of storage and multiple GPU cards, multiple FPGA cards, all of them interconnected here. You can do kind of a high performance computing here by using a kind of a single node, a single platform that you have in the market today. It's quite a lot of powerful devices are coming up in the market today. Equally important is that there are newer programming models coming into picture. I'm giving an example here of what Intel is doing. So they have this platform, they have this abstraction here called One API, meaning that you write your program once in C++, for example, and then you provide directives inside that so that you can compile that same code into various hardware units you have, the processors, the GPUs, and the FPGAs, whatever other accelerators you have. In fact, we don't have to be limited to these kinds of three kind of processing kind of abstractions we have. One could also look at other kinds of accelerators. There's various other accelerators coming in the market today. And this One API programming model provides kind of a uniform interface between them here. The One API here is that you write your program and you can compile that. In fact, we have been using this platform, this One API. You can write C++ code and then specify part of the code and say, look, I want this part of the code to run on an FPGA, compile that for FPGA. So all that stuff about Verilog and worrying about the virtual overlay architecture, it's completely hidden from you. If you want to get extremely high performance, we do that. We understand FPGAs, but if you are a user and then you are coming and saying that, look, I have a code that's got some serial program, I want multiple nodes, multiple threads, and then I have a data parallel portion of that goes on the GPU, whatever you're doing on the GPU, for example, and some other portion, maybe it is not really that looks that attractive for GPU or CPU, put that on an FPGA accelerator. You could specify in this uniform way, and this compiler and runtime system will handle that for you. And it also deals with a unified shared memory for that. Like if you look at OpenMP programming models, we are used to this concept of external memory that is shared. Sometimes you're also used to the notion of a distributed memory that is shared across the various resources you have. You can specify all that as part of the One API. You can specify what is going to be stored if you wish to in the local DRAM of the FPGA. So you can do that partitioning as well, or you can put them in the global memory of the processor, CPU, the processor, GPU, and the FPGA. All that can be specified as part of the One API interfaces we have. It gives a very nice global view of the whole hardware, whole system you have, and you can experiment. You can write a purely heterogeneous programming code today by using an interface like this. So you can go between various hardware units, various platforms you have here. So I talked about some memory sharing mechanisms. If you're coming from scientific computing, we are used to using message passing quite a bit, large-scale clusters. This programming model also provides this message passing. In fact, you could do the send-receive commands between the processor and the various devices. You have this interconnected on the PCI bus of that particular unit, or you can also do the shared memory at the node level inside those devices here. So let me conclude here. So the points I want to make, take-home points, this technology is there. It's evolved, it's available, it's usable, it's fun to use it. It's something that I strongly advise you to try it out if you have not tried it. You don't have to do very long hardware programming. You can get access to these machines very easily on the internet today. Memory and interconnect for these technologies have dramatically evolved. You can get extremely high performance, low latency, accelerated performance on these implementations. Processor and FPGA communication. The idea of the CXL, CCIX I talked about, standards have evolved, so you can directly connect between them and make use of them. Heterogeneity is built into these kinds of newer devices in the market at the node level, at the chip level itself. And if you're looking for low latency implementations, applications, there's a lot of potential here in this technology. In fact, whether you should be using FPGAs or GPUs. So I organize this large FPGA conference. It's going to be in the month of May in Los Angeles area. It's called FCCM. In fact, we are organizing a very interesting panel in that. So if you want to do low latency, large language models, what is the technologies to use in that? Should we be using FPGAs, GPUs, or accelerators? So we're inviting people from, in fact, we have accepted panelists from Intel, AMD, Cerebras, from Amazon. We're going to debate this. What is the role of FPGAs in this new space of ChatGPT and those kinds of very, very large models? And then you're focused on inferencing. Training is a different problem altogether. There are different set of issues in training. So if your interest is low latency applications, and what is the role of accelerators, what is the role of FPGAs in relation to what is happening in GPUs, and what is the role of these technologies if for you the power efficiency is also important. So I talked about earlier in terms of the energy dissipation in this. If you get the highly optimized designs on these platforms, in addition to the 4x improvement, I talked about 100 watts versus 400 watts, you can get very highly optimized implementation of FPGAs, which can give you very high performance. So let me stop here. This is my team. So again, whatever I presented is joint work with my students, my postdocs, and other faculty that's involved in my research. So let me stop here if there are any questions. It's a good question. So just to do some comparison between the power dissipation, that's a question here, compared to baseline CPU implementations. So there are two power dissipations you need to consider obviously here. One is what is happening on the processing side, it's a CPU or GPU or the FPGA. The other is on the memory side, on the DRAM side here. So there are applications in which you have extremely large DRAMs that you make use of there. The DRAM power dissipation could be significant in those applications. So what I mentioned here in my presentation today is the processing power dissipation. Just take the raw compute power of the FPGA and the CPU and how much power is dissipated. The peak power dissipation of the FPGA is approximately 1/4 of the peak power dissipation of the CPU. That's kind of the raw numbers. Just look at the data sheets and compare them. But the good news from FPGA point of view is that typically you don't consume the complete FPGA resource, all the SRAM, all the logic units, all the memory, all the communication channels you have in that. So you get a much higher performance from the processing side of the FPGA. Compare that with the CPU and the GPU. That is the kind of numbers I talked about earlier. So if you do, for example, the graph analytics problems, if you actually just implement the FPGA, the virtual overlay architecture I talked about for the edge-centric computing paradigm that we had here, the performance improvement on the FPGA side, you can get those FPGA implementations for the same problem, but we can run the FPGA for about 50 watts or so compared to what happens on the CPU side, which could be taking all the way up to 400 watts of power. And then when you make those comparisons, we are running the CPU portion with all the cores used. That's what is the baseline comparisons that we perform there in those implementations. So if you compare the pure FPGA power and the CPU power, we're talking about a factor of 8 performance improvement. That's for the actual implementation for the graph analytics problem. I think there is one important metric here, which is there is you're not designing an ASIC, you're designing using the FPGA. So there is a trade-off here. I got a lot of programming, I got a lot of productivity, If I were to design an ASIC for the same graph, and in fact, there are companies that do that, actual ASIC for that, the performance is much higher in terms of the power performance. But it comes at the expense of the additional work you have to do as design time. So I think that's the trade-off here. So going from the CPU to FPGA, you got performance improvement, but that's not good enough for certain applications. That's kind of the hypothesis here. Particularly for edge applications, it's even 50 watts is quite a lot of power. It's not allowed. Even a 1 watt of power is quite a lot. So I think where the technology is evolving today, there are, if you go to vendors like Intel, and you tell them, look, I designed whatever is your application, I designed it, it's good, I get performance in terms of power and performance, I have latency is good, power is good, what can we do next? But I want this 50 watts is not good enough. So there are technologies in the market today which I did not get into, which I don't work in that space, which what they do is that they take the FPGA technology, and if you go and tell Intel, I want to buy 100,000 units of this, and can you give me something that is 10 times better than this, 10 times better in terms of the power performance product. And these technologies exist in the market today. And then they are not commercial in the sense of I buy a chip and use it. You have to go to, and there are software tools available. In fact, Intel does it, AMD does it, where you can further get performance if you're willing to put the front end cost for it. Some of the ASIC design. And that's what you are not putting that cost. When you buy a $1,000 FPGA chip, all the design has been done for the chip. That's an amortized cost you're paying once. But if you want to get the ASIC version of that, it's doable. You can get a higher performance in terms of both the power as well as the latency at an extra cost, design cost. Please. Right. Right, right. Right. Yes, yes, yeah. So I think whatever I've done here is that I used as an infrastructure in my work here, but you can get them as a service. In fact, there is a lot of trend towards whatever service I talk about on the FPGA itself is provided as a service available in the cloud platform. So you don't have to worry about the underlying hardware at all. You can just get it as a service. I want to accelerate something. I want to do recommendation systems. I'm willing to pay this much money for this much latency, and can you give it to me? And if you go talk to Amazon, they may not even tell you what the underlying hardware they are providing for you, running on the CPU or a GPU or the FPGA, depending on your requirements and how much you're willing. So from my point of view, we are developing accelerators. So we look at it as platform as a service for our implementations. But from a real end user point of view, you don't have to do the optimizations that I do as a researcher, my interest here. So you can get them as a service. So I think the best way to handle that question, handle that kind of a problem would be if you go to, let's say, going between Intel and Xilinx is it's a different game altogether. Take a particular design, I want to do it. And the high-level synthesis commands for Intel and Xilinx are different. Even though we say it is like OpenMP style. They all provide pipelining, loop, all that is there, but you have to learn the syntax to be able to use it. So will the program that I run for a particular device category in Intel, can I reproduce the same thing on a device? That's a challenging problem. But that challenge exists in the GPU space as well as in the processor space. Right? Today we talk about RISC architectures becoming popular. Can you run a program that runs on C++, on x86 and just transport that RISC architecture? Everybody wants to claim it's doable, but can you do it all the time? Right? Now I got my notebook and I like to use the Windows Surface notebook. When you go and buy Windows Surface, Microsoft has their own processors available. If you see the fine print in that, it says not all applications will compile into that particular processor Microsoft is using, which is not x86 processor. That's the reality of it today, reproducibility, right? So if you go to the hardware space and then ask AMD or Intel, can I run the same Verilog code or same thing for various devices in your family? It's a tough question. It's just too much happening. But what you can do today, in the same family, you can do backward compatibility. HighLevel synthesis tools provide you that. So if you go to Zinc, there's a set of tools you can use, or if you want to go to the data center cards, you can get those compatibility within those device families, U250 or whatever. It's a category of devices that are available in the center. So I think this is an interesting question, but I think this problem exists everywhere. Now we ask a very simple question. AMD has one of the largest supercomputing installations, the top machine, top 500, right? They have the AMD MX or MX100 is the accelerated data parallel engine. It's a GPU. I have a GPU code. Will that run on an AMD GPU or an Intel GPU? It's data parallel. It is CUDA-like. It's not exactly CUDA for Intel or for AMD. It's a reality of today. Get that, everybody talks about every Tom, Dick, and Harry is doing a GPU today. Will the same interface work? The answer is no. So I think the problems is much harder in the FPGA space, but I think we made a lot of progress in that. So of the compatibility, backward compatibility tools. Believe me, 10 years ago, we used to write this Verilog code, synthesize it. I know those expressions may not make any meaning to a general computer science audience. Synthesize it, do place and route. Actual physical mapping from that software, actual hardware device you have. And that's what we do for a living. That's as PhD students, my students do all that. But it's a lot of compatibility issues there. These tools are, they're all specific to a hardware. Right, to get performance and compatibility and reproducibility in that context is a tough. So it's a good question. It's a challenging question. I think the community is making progress, but the community is not to make a fair comparison with the general purpose software community. I think this problem exists in everywhere, right? So ideally, I would like to see the next few years that whatever code we wrote for an NVIDIA GPU runs on an Intel GPU or an AMD GPU. Just want to use it. If it happens, everybody will be happy. Chances are, I don't know. So I think there are two important directions the community is exploring. In fact, there is a very interesting line of research in the FPGA space in which FPGA hardware itself should be made open source, right? Whatever hardware architecture we have for Intel or AMD, there are projects in the US, open FPGA forums in which the hardware itself is made open, right? Plus, on top of it, you want to build completely modular and tools for all this synthesis from high level. There are interesting projects like this, hardware software tools that are available, which are completely open source. So if you are concerned about extremely high performance you want to get, this is not the way to go. But you want to have a completely open hardware, open software. There are research projects of this nature which do this complete open source hardware, open source software. It's totally new. It's not like Intel says x86 below that layer is completely, I don't tell you what's happening here. Everything is open to you, the hardware. Can you build software for that? Can you build tools for that? It's a very interesting research challenge. This is happening to the market. It's a complete open hardware and software for FPGAs. It's a good question, yeah. You want me to give a short answer? I'll be shorter than your question, I'll promise you. That's a very loaded question here. To give a short answer to that, I think first of all, FPGA's technology has matured quite a bit. I think the important thing I notice here when I give talks or when I meet people is that people are not aware of it. People are aware of GPUs. For the last 20 years, NVIDIA has done a great job in terms of publicizing, giving free to university. I'll give you a card for free. The AMD and Intel have not done that to that extent. But FPGA technology is mature today. Technology is mature. In fact, I said some of the FPGA devices are probably even more denser than the CPUs and GPUs in the market. In terms of the packaging density, in terms of the number of transistors, the area of those devices, they are quite dense. It's a very mature technology. I think where the issue is in terms of the software, we discussed that, high-level synthesis, integration. There's a lot of work to be done there still, even though we have come a long way in the last 25 years in that space. And then if the issue is that can we use the full 200 gigabytes per second kind of a bandwidth? There are applications, people are interested. In fact, people have built such kind of devices, such kind of platforms in the market. And the graph analytics is an example of that, where the higher the bandwidth you give me, the better I can do. If I can only program those FPGA devices, that's what we did, that we can completely use the bandwidth. So there's a lot of potential if there are those kinds of optically interconnected devices. In fact, there are a lot of test benches of that nature in the US as well, where the goal is to really completely exploit the bandwidth as opposed to just the pure compute power we have. And look out for the graph analytics area, graph machine learning area. We have not done there. There's quite a lot of challenges in that space. Quite a lot of companies producing hardware, producing software in that. At IPDPS this year, one of the keynote speakers is talking about graph analytics, what's happening in parallel programming in the last 50 years. And we also have a speaker from AMD who's actually answering some of these questions. What is the future of these kinds of integrated platforms with FPGAs, GPUs, and CPUs, high bandwidth connects? Okay, stop here.